Welcome to the debate. So imagine an artificial intelligence that knows you are going to develop a severe heart arrhythmia, and it knows this 3 weeks before you feel a single palpitation.
Right, before you even realize anything is wrong.
Exactly. And, it doesn't know this just by looking at your resting heart rate. It knows this by cross-referencing the continuous data from your smartwatch with the micro-fluctuations in your city's air quality, your midnight snacking habits, and specific genetic markers in your saliva.
It's a massive scale of surveillance, really.
It really is. Today, we are exploring the emergence of AI as a tool to cross-reference and integrate this massive, multimodal biological data. We're talking about everything from genomics and microbiomes to continuous glucose monitors and environmental sensors.
And the stakes here are incredibly high. We are looking directly at the source material on global AI health deployment to answer a central question. Does AI's ability to fuse petabytes of high-dimensional data fundamentally master biological complexity to deliver reliable, democratized predictive health?
Or conversely,
Right? Does this massive data integration create fragile systems that are prone to spurious correlations, amplified biases, and, honestly, the dangerous over-medicalization of normal human variation?
well, I will be arguing that multimodal AI successfully circumvents human cognitive limits and the mathematical curse of dimensionality. By doing so, it turns deeply fragmented biological data into actionable, life-saving foresight.
And I will be arguing that relying on these interdependent exabyte-scale data streams introduces dangerous vulnerabilities. It risks mistaking environmental noise for actual disease, and it threatens to over-pathologize global populations by, treating the human body as an endlessly optimizable machine.
To start, I think we have to recognize a fundamental flaw in traditional medicine. It isolates data.
Completely.
It silos it, yeah.
Right.
If you have a heart issue, a cardiologist looks at your EKG. If you have a blood sugar issue, an endocrinologist looks at your glucose levels. And as a result, the medical system frequently misses the intricate systemic links.
For sure.
Like, for example, how poor sleep architecture elevates cortisol, which in turn spikes blood sugar, which subsequently strains the cardiovascular system.
I agree that the human body is deeply interconnected. It is the absolute definition of a dynamic, nonlinear system. Small inputs can create massive, unpredictable, cascading effects.
Exactly. But human cognition simply cannot process the thousands of interacting biomarkers that drive complex diseases like cancer or Alzheimer's. The human brain can maybe hold, 5 to 7 variables in working memory at once?
Sure, the cognitive limit is real.
But modern AI architectures, specifically multimodal transformers and graph neural networks, or GNNs, they solve this by fusing orthogonal data streams. We are talking about models pairing retinal images with genomic SNPs.
Single nucleotide polymorphisms?
Right, those tiny, individual variations in your DNA. AI pairs those to predict diabetic retinopathy. We're analyzing millions of continuous ECG patches against Beijing air quality data to assess arrhythmia risks.
Look, I will readily acknowledge the mathematical elegance of these AI architectures. Tools like convolutional neural networks, which revolutionized image recognition, or autoencoders that compress and denoise data. They are brilliant pieces of computer science.
They're revolutionary.
Mathematically, yes. But we cannot forget that biological organisms are not just complicated, they are complex. Massive data fusion in these dynamic environments often amplifies noise rather than signal.
How so?
Well, finding a mathematical pattern in a high-dimensional space simply does not equate to clinical reality.
Let's unpack that, because I think it gets to the heart of the technical debate here. Algorithmic power versus the threat of spurious correlations. In traditional statistical methods, when your variables outnumber your samples, you hit something called the curse of dimensionality.
Right, the math just breaks down.
Exactly. If you are tracking 10,000 proteins in the blood, but you only have 100 patients in your study, traditional math buckles. You can draw a line connecting almost any dots in a space that vast, meaning most of your findings will just be random noise.
Exactly my point. The model just memorizes the noise in the training data instead of learning the actual underlying biological rules.
But modern AI architectures inherently overcome this. Let's look at the EMPA-REG trials detailed in the material. Transformers were able to predict kidney decline by analyzing over 5,000 different features of proteins in patient urine.
Wow, 5,000.
Yeah, and how did it not get lost in the noise? Because transformers use what's called an attention mechanism. Instead of weighing every variable equally, the model learns which specific combinations of proteins actually interact and matter. It puts a mathematical spotlight on the relevant pathways.
Okay, but
And then you have graph neural networks, GNNs. They are modeling the human body as a literal network.
let's pause and clarify what a graph neural network actually does for our listeners, because it sounds, frankly, incredibly abstract.
Fair point. Think of a graph neural network like a transit map of a city. The organs or the specific proteins are the nodes, the subway stations. The metabolic pathways or blood flows are the edges, the train tracks connecting them.
Okay, I follow.
So a GNN doesn't just look at a list of numbers. It maps the topology of the body. It can physically track signals like inflammation moving from the gut microbiome directly along the vagus nerve to the brain. This is a level of biological mapping that was computationally impossible a decade ago.
That is a very compelling way to visualize it. But I have to challenge the clinical validity of these emergent patterns, because I'm sorry, I just don't buy that every connection a graph neural network finds is biologically meaningful.
Why wouldn't it be?
Because the material explicitly warns us about confounders. Take the Delhi datasets mentioned in the text.
Oh, right, the air pollution data.
Yes. In a highly polluted urban environment like Delhi, poor air quality correlates with almost everything. Respiratory distress, heart rate variability, even dietary changes because people stay indoors. The AI looks at that massive web of data and can perfectly mimic a disease signal, leading to spurious correlations that the system flags as a health crisis.
Sure, but
The AI doesn't know what pollution is. It just sees numbers moving together.
researchers don't just blindly trust the black box anymore. They use explainability tools.
You mean tools like SHAP or LIME, but we need to be very precise about what those tools actually do. Let's explain how they work.
Sure.
SHAPE and LIME do not crack open the black box and give you a biological mechanism. Mathematically, they just prove that a simple, understandable function can approximate a highly complex function, but only locally.
Meaning, they explain exactly why the AI made a specific decision for a specific patient, even if they can't explain the entire global model at once.
Right. It's like taking a magnifying glass to a massive, wildly curving 3D mountain range and saying, look, right here in this 1 square inch, the ground is flat.
That's a bit reductive.
It tells you what the model did mathematically in that tiny, localized instance. It does not prove a physiological truth. You are mistaking a mathematical artifact for a biological law.
I see why you think that. But let me give you a different perspective. Looking at isolated biomarkers is like listening to a single violinist and trying to judge the entire symphony. Multimodal AI hears the whole orchestra.
That's poetic, but
And with graph neural networks, it goes even further. It sees the sheet music, the acoustics of the concert hall, and how a mistake in the brass section physically ripples over to the strings. It doesn't just find an artifact, it finds the interplay. And the technology is actively evolving past the mere correlation you're worried about.
how so? Because correlation is the fundamental bedrock of machine learning.
Not anymore. The material introduces a profound shift called causal AI, which utilizes a mathematical framework known as do calculus.
Do calculus, right?
Yeah. Instead of just looking at historical data and seeing that two things happen at the same time, like, noticing that ice cream sales and sunburns peak together, do calculus allows the AI to mathematically simulate an intervention.
Simulating interventions.
Yes. It asks the data, if I actively intervene and force a change in variable X, what happens to variable Y? It separates the actual root cause from the background noise. It's a mathematical guarantee designed to filter out the exact spurious correlations you're worried about with the Delhi pollution data.
I understand the immense theoretical promise of do calculus, but causal AI, no matter how sophisticated, is still fundamentally blind without the right map. Which leads us to a crucial issue. We can debate how beautifully these algorithms process data all day, But we have to look at the nature of the data itself. Whose biology are we actually modeling?
That is a fair pivot. And I would argue that AI is exactly the tool that democratizes this foresight globally. Historically, you are right. Medical data has been siloed in wealthy Western institutions.
Entirely.
If you didn't live near a major research hospital, your biology wasn't studied. But AI solves this through federated learning.
I want to make sure we explain federated learning clearly, because listeners might hear that and picture a giant, insecure database in the cloud sucking up everyone's private medical records.
Exactly. And that's the brilliance of it. It's the exact opposite of that. In federated learning, the raw patient data never leaves the local hospital. Instead, the AI model travels to the data.
Okay.
It trains on the local hospital's secure servers, learns the underlying mathematical patterns, and then only those insights, the updated weights of the algorithm, are sent back to the central cloud. It solves the privacy bottleneck.
So it aggregates insights without aggregating raw data.
Precisely. And the source material highlights incredible successes here. Look at Brazil's Fiocruz network. They used federated learning to pool insights from 50 million patient records across the country to predict insulin resistance related to polycystic ovary syndrome.
That's a huge data set.
And in Indian urban slums, apps like Beto are fusing smartphone camera data with simple blood diagnostics, and their models are actually outperforming standard diagnostic criteria. We are even seeing edge AI, where the processing happens entirely on the device without needing the cloud, bringing analysis to incredibly remote areas.
Like what?
They're using smartphone accelerometers and voice analysis to detect Parkinson's tremors in rural Mongolia. That is the very definition of democratizing healthcare.
Democratization in theory, perhaps, but the foundation of the data is deeply structurally skewed. The source material presents a stark reality that we cannot gloss over here.
I'm not glossing over it.
Well, 80% of the training data driving these global AI models is heavily skewed toward Caucasian populations. If we look at bacterial DNA analysis for microbiome research, the global databases are 90% skewed toward gram-negative bacteria.
But the algorithms are adapting to...
Let me finish this point, because the clinical consequences are severe. We know for a fact that these models falter on African genomes. Why? Because they fail to account for specific regional variants, like the APO1 genes associated with nephropathy.
Right.
The model literally doesn't know those genetic variables exist because they weren't in the training data. 3 billion people globally face absolute data poverty.
I don't dispute the data gap, but the tech industry is actively solving it.
They are trying to solve it, but look at how. When they try to fill those gaps, they rely on behavioral proxies. They use cell tower mobility data to infer the health behaviors of a population that doesn't have smartwatches. That doesn't democratize health. It just introduces entirely new systemic errors disguised as high-tech solutions.
But if the data is incomplete, shouldn't we rely on the computational solutions the material provides to fix it? We aren't just throwing our hands up and accepting the missing data. The text explicitly outlines the use of generative adversarial networks, or GANs.
To generate synthetic data.
Yes, and we should explain how clever this is. A GAN consists of two neural networks playing a game against each other. One network acts as a forger, trying to create realistic synthetic patient profiles, say simulating the metabolic profile of a South Asian patient.
And the other?
The other network acts as a detective, trying to tell the fake data apart from real data. They loop millions of times until the forger is so good that the synthetic data is statistically indistinguishable from reality. This is actively being used to correct the exact regional biases you're talking about.
Indistinguishable mathematically, maybe, but a synthesized South Asian profile generated by a GAN is still a mathematical simulation. It is an algorithmic best guess based on the existing skewed parameters the model already has. It is not a real human being living in a real complex environment.
Then look past GANs to the rise of foundation models. The material discusses Meta's ESM model. This is a massive AI that pre-trained on 2.5 million bacterial proteins. And here is the aha moment. It can now perform what's called zero-shot prediction.
Zero-shot prediction, meaning it hasn't seen the specific data before.
Exactly. It means it can accurately predict the function and folding structure of a protein sequence it has never explicitly seen before. How?
because it didn't just memorize the training data. It learned the fundamental evolutionary grammar of biology. Just like learning the rules of English grammar allows you to write a sentence you've never read before, these models are learning the rules of biology, which transcends regional data poverty.
Learning the grammar of biology in a controlled computational space is one thing. But that distinction matters profoundly when we transition from the integrity of the data to the actual clinical application.
Right.
What actually happens when we take these predictive models with their synthetic data and their mathematical assumptions and unleash them on everyday patients?
What happens is we unlock immense preventive power. For decades, the entire medical system has been stuck in a reactive paradigm. We wait for the heart attack to happen, and then we treat it. We wait for the fasting glucose to hit diabetic levels, and then we prescribe insulin. Multimodal AI shifts us entirely to prevention.
Prevention is a noble goal, but how exactly is it executing this?
The material cites a fascinating 2024 Mayo Clinic study. They used LSTMs, long short-term memory networks. Now, traditional neural networks treat every data point independently, but an LSTM has a memory cell.
So it tracks changes over time.
Yes, it is specifically designed for time series data, meaning it remembers what your body was doing 10 days ago and contextualizes it with what you were doing today. Using LSTMs, the Mayo Clinic was able to predict underlying insulin resistance using just 14 days of standard wearable data.
Just from a smartwatch?
Exactly. Heart rate, sleep stages, movements. And the scale of this is staggering. A recent Lancet meta-analysis of 50 different trials showed that early AI detection averts 40% of type 2 diabetes cases purely through personalized lifestyle nudges.
40% is huge.
Imagine the global impact of that. We have apps now that deliver a daily metabolic score. It empowers an individual to make small, life-saving adjustments. You wake up and you know exactly how a weekend of carb loading and poor sleep affected your unique, highly personalized insulin resistance index.
And that daily score is exactly where the clinical risks terrify me. We need to talk about the reality of this constant and inescapable surveillance. You're talking about giving perfectly healthy people a daily score on their metabolic worth, based on their midnight snacking and their sleep architecture.
Well, information is empowering. It allows people to take control. But the text explicitly warns us, not all resistance needs drugs. When you build a system that constantly churns out probabilistic risk scores, you create an overwhelming clinical urge to act.
Not necessarily. The medical system does not operate on passive awareness. It operates on intervention. If an AI flags a 5% increase in a patient's probabilistic risk for metabolic syndrome, we are going to see the preemptive overprescribing of GLP-1 agonists, like Ozempic, to people who do not actually need them. We are treating the human organism as an endlessly optimizable data stream.
That's an interesting point, though. I would frame it differently. The AI isn't forcing a prescription, it's highlighting a trajectory. It's up to the clinician to decide if that trajectory warrants a pharmaceutical intervention or just, a walk after dinner.
But you are assuming the algorithm understands context. It doesn't. And we risk over-medicalizing perfectly normal, traditional lifestyles in the name of algorithmic optimization. The material brings up a vital, concrete example of this, regarding the need for community-led validation in Indigenous Australian groups.
Right, because the models were trained on Western baselines.
Exactly. Their physiological data and lifestyle patterns were being repeatedly flagged as abnormal by Western-trained algorithms. It threatened to pathologize a traditional way of life that has existed healthfully for millennia. When an AI lacks cultural and clinical wisdom, it treats standard human variation, a statistical deviation from the Caucasian mean, as a disease to be cured.
I concede that the psychological burden of false positives is a real concern. No one wants a smartwatch dictating their anxiety levels, and no one wants a cultural lifestyle categorized as a medical anomaly by a server in Silicon Valley. But the material explicitly features hybrid human-AI loops designed to prevent this.
How does a hybrid loop solve the problem of a fundamentally skewed baseline?
By ensuring the AI is an assistant, not an autocrat. The models are designed to refine these thresholds over time through human feedback. The AI processes the petabytes of data and flags the anomaly, but the human clinician contextualizes it.
If they have the time.
The clinician looks at the indigenous patient and says, "This isn't a disease state. This is a regional baseline. That feedback is fed back into the model to adjust its weights. It's explicitly designed to prevent the very over-medicalization you fear, ensuring that we use the data to nudge lifestyle choices appropriately.
A hybrid loop sounds wonderful in a well-funded research hospital, but it assumes a human clinician has the time, the diagnostic resources, and the statistical literacy to successfully override a petabyte-trained AI model. In an overburdened, understaffed global health system, a doctor seeing 40 patients a day isn't going to debate the nuances of an LSTM's probabilistic output. The AI's prediction will just become the default diagnosis.
Well, we have covered a tremendous amount of ground today, and we are coming up on our time. To summarize my perspective, yes, biological data is inherently noisy, and the human body is vastly complex. But AI's unique ability to harmonize these modalities, from single-cell RNA sequences to continuous environmental sensors, offers an unprecedented, mathematically rigorous escape from the reactive medical paradigm we've been trapped in.
A paradigm shift, essentially.
Completely. By utilizing mechanisms like attention in transformers and the topology mapping of graph neural networks, it is actively solving the curse of dimensionality. It is securely scaling across borders via federated learning, preserving privacy while aggregating wisdom. And despite the hurdles, it holds the genuine promise of democratizing predictive health on a planetary scale.
And from my perspective, the premise that we can master biological complexity purely through massive data fusion remains a deeply fragile foundation for global health. The human organism is not just a math puzzle waiting to be solved. Until we fully resolve the structural gaps in our data, like the massive underrepresentation of global populations, and until we curb the clinical urge to over-medicate based purely on probabilistic risk scores, we are simply building a highly sophisticated house of cards. Treating variations in human life as deviations to be endlessly optimized is a perilous endeavor.
The tension between computational pattern finding and actual clinical wisdom clearly remains an open, critical frontier. We highly suggest our listeners dive into the source material themselves, as there is much more to explore. We didn't even get to touch on the evolution of dynamic consent models for patient data, or the fascinating future of quantum AI simulations in biology.
There is certainly no shortage of complexity ahead, and the math is only going to get faster.
Indeed it is. As we said at the start, when you zoom out from the isolated specialist and look at the whole interconnected system, the picture becomes incredibly complex. The question isn't just whether AI can hear the whole biological symphony, but whether our medical systems are truly ready to understand the music. Thank you for listening.